The declaration of a leftist tree node is simple. So we have the normal element field plus 2 pointers, the left pointer and right pointer, plus an integer variable called the NPL, records the now pass length of each node. And let's see how merge is done. First, recursively. So these are the two min heaps given. We're supposed to merge them. First of all, tell me which element is supposed to be the final root of the resulting heap. 3, right? How do we know? Because the resulting heap is supposed to be a min heap, and the root of the final min heap is supposed to contain the smallest key, right? So what we do is we compare the two roots and keep the smaller one unchanged, and we're supposed to change the other one. Okay, so what we do is we merge heap 2 with the right subtree of heap 1. So recursively merge these two heaps. So step 1 is we're supposed to merge the right subtree of H1, this one, with the second heap, this one. And since this is done recursively, I'm just showing you the final result here. So you can understand recursion as a kind of magic box, right? And we just send in two heaps, one with a smaller size, but it doesn't matter as long as there are two heaps given to this function merge. It can solve the problem recursively. You don't have to actually care about how it is done. You just trust it. Trust it to be able to return to you the right answer. Okay, so no matter how it is done, they are merged into one leftist heap. Okay, so the next step is to attach the new H2 to be the right subtree of H1. So to attach this result to be the right subtree of H1. And here we go. Just by looking at this tree, we can realize that obviously it is not a leftist heap, because obviously the now pass length of this root is larger than the now pass length of this root. Okay, and so what can we do? Simple, right? Just check the now pass length. If it violates the property, just swap them. Swap the right child with its left child. That will do. Now let's see how to write the programs. Why don't you just pause video for 2 minutes and read these two pieces of pseudocode by yourselves first, and then we're gonna go through them line by line all together. So are you done? Okay, so this is a very interesting form of recursion. We don't see such kind of recursion very often. It's like merge is the interface. Okay, we enter this function merge, and it calls merge1. And within merge1, we call merge. So these two functions are calling each other recursively. So basically, what this function merge does is to first handle the smallest cases, right? To implement a recursive function, one most important thing is to define the return cases, or say the simplest cases, so we can begin to return, to jump out of recursion and begin to return, right? So the simple cases are if one of the heaps is empty, we simply return the other one. Okay, and this step guarantees that whenever we enter this function, we just make sure that the first root is smaller than the second root, right? To check here, if the first root is smaller than the second root, we call merge1 with H1 first, H2 second. Or otherwise, if h1 is greater than or equal to h2, h2 is smaller, we call merge 1 with h2 first and h1 the next. Now let's enter merge 1. First, there's another check. If h1 has no left child, then it must be a single node. Why? Since h1 must be a leftist tree, right? If it has no left child but one right child, it will certainly violate leftist property, and therefore that's impossible, right? So if it has no left child, it must be a single node. Then what we do is simply to attach h2 to be the left subtree of h1. And the now pass length of h1 was 0, and it remains 0 after this step, right? So it will be silly to first attach h2 to be its right child and then swap its left and right children. It's not necessary, right? And if h1 is not a single node, if it has some left subtree, then that's what we do as we described before. We simply merge the right child of h1 with h2 and attach it to be the right child of h1. And then to compare the NPLs of its left and right children. If it's necessary, let's swap their children. And be careful here. Don't forget this one last step. We have to update the NPL of h1. Another question is, why do we only consider its right NPL? I mean, it's updated to be the NPL of its right child plus 1. Why not consider its left child? Because after this comparison, it's already make sure that its left NPL is larger than its right NPL. So it's sufficient to only consider the smaller one, right? One last question is, what if this NPL is not updated? What's going to happen? Well, think about it after the class. I'm not going to give you the answer here. Okay. And the time complexity is guaranteed to be log n, but it's not so clear if we consider this recursive version. It will be clear if we consider the iterative version. The iterative version, which is actually equivalent to the recursive version, but it's easier for human beings to understand, goes this way. Say, given two heaps. Step 1, we just sort the right paths without changing their left children. What does it mean? It doesn't mean we have to apply quicksort to sort the right paths. It's not necessary because we're talking about heaps, right? In any heap, it's guaranteed that all the paths from the root to a leaf node contains a sorted sequence, right? So their right paths are already in sorted order. What we actually do is we just merge the two right paths. So at the very beginning, we have two pointers pointing to the two roots, and we just compare the two root keys and keep the smaller one. Okay, so we keep the smaller one, and then to move the first pointer along its right path down to its right child. So the first pointer points to 8 here, and then we begin to compare these two keys and realize that 6 is smaller, and therefore we keep 6. Next, we're supposed to compare 7 and 8. 7 is smaller, so here is 7. And next is going to be comparing 8 and 18, so here is 8. All right, and finally, we attach 18 as the last node along its right path. So this is step 1, but obviously this is not a leftist tree. So what we do is we begin to update the NPLs along the right path from bottom up and swap children if necessary. So while we are updating NPLs from bottom up, this one is not changed, and this one is okay, but it's not okay for the node 7, right? And if we check 6, although it looks like this is heavier, but actually the now pass length is not very long in its right subtree, so this one is fine, but the root is not fine, and therefore we must make 2 swaps. First, to swap the left and right children of 7, and finally swap 10 with 6 and obtain the final result like this. So you see that the iterative version is much easier for us to understand that what is really going on during the merge process. However, on the other hand, if you really want to implement this iterative version, you're going to see how difficult it is. It's going to be much more complicated than the simple recursive version. All right, and according to this iterative version, we can clearly see that everything is done along the right paths, right? So the worst case time complexity is proportional to the sum of their right paths, where for each leftist heap, its right path is just log n, this is another log n, so to sum them up, we still get a log n time bound. But another question for you to think about is, we ought to be careful here. The question is, can you be sure that this iterative version is equivalent to the previous recursive version? So can you be sure about that? Think about it, okay? Although it's not so hard to prove that they are actually equivalent. So the answer is yes, which means that since we can clearly see that the iterative version gives log n upper bound, it's guaranteed that the recursive version also runs in log n time. Okay, and so much about the merge. And the other function is deletion. It's the delete min function, which is actually quite trivial. If we know how to do merge, delete min means to delete the root, right? After the root is removed, what do we get? We're going to obtain 2 separated leftist heaps, right? And what do? Merge them, right? So it's very simple. For delete min, step 1, we just delete the root. Step 2, we just merge the 2 subtrees. And obviously, the time complexity would be log n.